Hi, I'm Alex. I'm a senior simulation engineer at Technia. I work as a simulation consultant and I also support our simulation software customers and deliver training. Welcome to the third MODSIM episode. In this episode, we'll be discussing materials and non-linearity in finite element analysis.
Hi, I'm Robin. I'm one of the senior design engineers here at Technia. I help customers develop their ideas from ideation through to product creation.
Hi, Robin. How can I help?
Hi, Alex. I'm working on a design that I think could benefit from some basic FEA in the early design stages, and I've told you might be able to help me out with this.
Yeah, I'm sure I can help with that. Where have you got to so far?
So I've designed a concept housing assembly, which is held together with cantilever snap fits, both parts of which are made from a polymer. And I wanted to make sure that the components won't fail during assembly. I'll just share my screen with you so I can show you what I'm talking about. If you don't mind having a quick look. So the housing, as you can see, has two components. It's got the lid and the base. The lid itself locates around the perimeter of the base, and the snap fits are used to hold the parts together. I'm going to do some hand calcs first of all, but this requires Young's modulus. I'm using a grade of nylon 6, and I thought that had a non-linear stiffness. Do I need to account for that?
Yeah, you're right that polymers in general often have a non-linear stiffness, but that doesn't mean we can't idealize some of them as being linear below the yield point. We can't do that for hyperelastic polymers like rubber, because they have a highly non-linear response. But for a polymer such as nylon 6, it's common to select the yield point from the stress versus strain graph and then create what's called a second modulus using that point. So it should be fine.
Okay, so I have the data sheet and it does include the Young's modulus. So I'm assuming that's what it's actually referring to.
Yeah, it should either be the second modulus or what's called the tangent modulus. They're calculated in slightly different ways, but whichever one it is should be fine for your hand calcs if you trust the source.
Yeah, so I've got the data sheet from a material supplier, so I'm confident that can be trusted. Considering that I also want to do some FEA to validate the hand calcs, would that modulus be okay for that?
Yeah, again, that modulus should be fine considering you're in the early stages of the design process. If the FEA were being conducted as part of the final design validation, there's a benefit to using the stress versus strain graph to select a modulus based on the strains you're expecting. But for now, the datasheet value will give you a good idea of the stresses.
Okay, great. That's good to know. Do I need any other material properties for the FEA?
Assuming it's static, you'll need at least the Poisson's ratio. So nylon 6 may have some rate dependency, but we can probably leave that for a later stage of the design process. You may need more information, but it will depend on your failure criteria. So did the customer tell you what their failure criteria is?
Yeah, they said their criteria is that they don't want any permanent deformation of the parts once assembled.
Okay, so we need to keep stresses below yield. So you'll need to know what the yield stress is. But in terms of the properties you need to enter into FEA, then all you'll need is the Young's modulus and Poisson's ratio in this case.
I assume that means I don't need the stress and strain data after the yield point.
No, not in this case, because if your stress exceeds the yield, then the part's failed anyway, and you'll need to change the design somehow and then run a new analysis.
Okay, do we need to analyze both the upper and the lower components?
I'd say at this stage of the design process, just modeling the cantilever arm is going to give you enough information. You know how far the clip displaces when it's assembled, so you can use an enforced displacement approach to load the part.
Okay. The FE software that I have access to only has a linear solver. Will that be okay, or do I need to send it to you so it can be run on a non-linear solver?
Okay, so in reality, all problems are non-linear, but the question is, can we get away with using a linear solver in our particular case? So to answer that question, we need to address the three types of non-linearity. So the first is material non-linearity, and we already know that you'll be idealizing the stiffness as linear, and you won't be including any plastic data, which would be non-linear. So that's fine. The second type of non-linearity is boundary non-linearity. This is where the stiffness of the structure changes as the boundary conditions or the contact conditions change. So as your model will only include a single part with no contacts, this non-linearity won't be present. And the final type is geometric non-linearity. So a linear solver will assume that the stiffness of the structure is equal to the stiffness of the undeformed shape, and it doesn't update the stiffness as the structure deforms. So this obviously isn't ideal because in reality, as soon as the shape of your structure changes, the stiffness also changes. You may still get away with the linear solver, but it will depend on the amount of displacement that you're seeing. So if your displacements are small, then the answer should be reasonable. Also, with this type of nonlinearity, we need to consider the nature of the loading. So, for example, let's say you have a pole that's fixed on one end, and with a vertical load acting down the axis of the pole and one smaller force acting horizontally to bend the pole. If you're using a linear solver, the vertical force will only ever generate axial stresses, and the horizontal force will only ever contribute to the bending stresses. If you were to use a nonlinear solver, however, as the horizontal force bends the pole, the vertical force will begin to contribute to the bending too, and that will result in a much higher displacement for the nonlinear solver. So in your case, you only have one load and the displacement should be relatively small. So this source of nonlinearity shouldn't be a problem either. And I think your linear solver should produce reasonable results.
Okay, great. That all makes sense and is very helpful. Thank you. I'll just run off and do the analysis now and get back to you if that's okay.
Okay, sounds like a good plan.
Hi, Alex. I've run the simulation model now. Just for a quick sanity check, what I've done is I've constrained the sides of the base where it's been cut to simplify the model. So that's completely fixed now. I've applied a fixed displacement to this face here, and also applied the appropriate translation. I've also applied a refined mesh around the key areas that we're critically looking at for our analysis. I've run the simulation now, and it's showing that the design will yield in the contact area for the fixed displacement, and it's also yielding close to the base of the arm where it hinges. Are the contact area stresses to be trusted?
No, probably not. They're probably artificially high due to the enforced displacement being applied there, so we can ignore them. Similarly, the stresses at the boundary conditions will probably be artificially high, but they don't look too bad in this model, and they're sufficiently far from the areas of interest that it doesn't matter anyway. The stresses elsewhere can be trusted though, so it looks like you'll need to change either the material or the geometry in order to get them below yield.
Okay, well, the material for this project has already been specified, but I do have another design idea that I think will negate this issue. So I'll update the design, run that one, and I'll let you know how it goes if that's okay.
Yeah, okay, sure. Speak soon.
So I've revised the design now, and the snap fits are now an L-shaped profile design. I've reused the defining constraints, loads, and meshes as we've previously discussed. The results on this one look much better. It's removed the stress concentrations around the hinging point. The stress concentration still remains around the contact area, but as you mentioned, the stress in that area is not a concern for us for this scenario.
Yeah, that looks a lot better. I can see some high stresses towards those back radii, but I imagine you can reduce that stress by making some minor tweaks to geometry. So I don't think you need to worry about that just yet.
Yeah, I agree. I'm confident with the results we've now got. I'm going to show this concept to the customer and make sure that it has their approval before I finalize the design and take it from there. Once that's all sorted, I'll contact you with a more detailed final design, and then we can run the analysis on that to make sure that we're confident that all the components are fully compliant to the specification.
Okay, yeah, that sounds like a good idea. I'll speak to you when you finalize the design.
Great stuff. Thanks for your help, Alex.
No problem. See you, Robin.